Okay, we're going to do a quick sort of video lecture here on Chapter 5. Now, as you're obviously aware by now, due to the coronavirus, we're going to move almost every class in Nova to an online format. And so, what we're going to do in this class is pretty much follow the same general approach we would use during a normal semester if, for example, we had a snow day. Now, this week, which is the for the class that would have met tonight, the 16th, would be week 5, and of course, classes on the 16th and 17th have been canceled. And the reason they canceled those was to allow us to have opportunities to do some additional training. So there'll be some minor changes made, and I'm going to sit down later in the week and take a review of the syllabus and see if there's some things I can do to make this class a little better in terms of its being completely online as opposed to partially. So what we're going to do today is we're going to look at Chapter 5, Working with Digital Geospatial Data and GIS. This will work out pretty nice when we compare it to the lab that you're going to do this week, which is another one of the Esri trainings where you sign in with your ArcGIS online account like you did for Lab 1, and you'll spend about 2.5 hours, maybe a little longer, going through a guided exercise that will do this. I'll also have some additional video links posted for some things that I want you to see, some basic introductory level GIS stuff that'll be helpful. And I want you to watch all the videos, and I will do this every week. I will provide the lectures like this, and we'll also set aside some time starting next week when the class would normally be held, where I will likely do either a Zoom conference where I am available to take any questions that you might have within the class, or we may actually do the lecture through Zoom. We'll see how that goes, and we'll play that out over the next couple weeks and see what works best. Hopefully, this coronavirus thing will blow over quicker than what they're saying it will now, and that we will actually get back to normal by the end of the month, in which case we'll only have a couple weeks like this and it won't really upset the dynamics of the course too bad. But if it does, we will deal with it, and we'll deal with it accordingly. Um, I decided to take this opportunity to give all the students sort of a hard reset. And what I mean is, I went back and looked at some of the assignments that were missed, like the labs and the quizzes and the exams. And if you missed one of these, basically what I did was I created another version of the thing that was missed. I only assigned it to the students who missed them, and then I made them available in an online format using some of the technologies that they put in place that will make it comparable to an in-class exam. So, without any more ado about that, I will be going over this chapter. I also want to point out that some of you, if you have issues and you don't have a computer at home and things like that, there are still computer lab resources that will be available on campus for students to come in and use should they need to. If that's something you want to do or something that you're going to need access to, send me an email and I will send you the information about where the lab is at and what hours it's available. Otherwise, um, stay away from campus as much as possible. And if you have any questions, send me an email. Again, don't expect to get a call back if you call my office phone, because obviously I'm not going to be there and there'll be some delay before I get that message. But in the meantime, have questions about something we're doing, send me an email and ask, and I'll get back to you in a day or two as time allows. And hopefully, like I said, this will all end sooner rather than later, and we'll get back to normal. If not, we will finish the class online and make the best of it. All right, let's get started. So what is a GIS? This is a really good question, and for some period of time, it was a hotly debated topic. And sort of the dividing line between GIS versus other just graphic programs like Publisher or PowerPoint was the ability to analyze information. Now, what we're going to focus on are the components and what actually makes a GIS, and we'll talk a little bit more about that. So, in general, they say, and this varies a lot depending on who you ask and how they break it down, but generally, a GIS is considered to have 5 components. It is a computer or hardware. There is some software or some designed prescribed mechanisms that the hardware applies. There is spatial data, and so when we talk about spatial data, again, this is information that has location relationships with it. So it's not just a count or a value; it's a count or a value at a location. And then there's these various procedures and processes. And so the procedures and the processes are the kinds of things that we can do with spatial data. And basically, the hardware runs the software to take the spatial data and apply the procedures as dictated by the analyst or user. And so this can change a lot in some contexts. Instead of procedures and processes, it's sort of it's often called analysis. User is sometimes referred to as the human component. Spatial data is always spatial data, and then software and hardware are pretty much universal in terms of this. There's also a couple of other things you'll come across from time to time. GIS versus GISci, Geographic Information Systems versus Geographic Information Science. These are argument-laden labels, if you will, within the geographic community or the geography community. They've spent a fair amount of time historically arguing and defining and trying to classify where and how things fit into this. We're going to stay above the fray, if you will, in this context. We're not going to focus on who's right and who's wrong in terms of whether we're teaching GIS or GI science. We're going to focus on making sure that you understand the systems and the science, and we're not going to get wrapped up in what we label it. So here would be an example of a GIS. This is the Mahoning County GIS Department. This is their page. This is a system that they're using. And it shows, that's the other thing. Anytime I do these video lectures, I yawn profusely, and I apologize for it. I've tried to do it in the morning. I've tried to do it at night. I've tried to do it in the middle of the day. I've drank coffee. I've drank Mountain Dew. I've had Red Bull. Nothing seems to help. Usually within 3 slides, I'm yawning. Sorry. I digress. So this is an example of a GIS, and basically what you have here is you have some hardware somewhere that's operating a set of software that generates this interactive window where we have spatial data that the user can access. Now, for it to be a GIS, we have to apply some sort of spatial procedure, some sort of analysis, whether that's creating and editing or doing other things. But that's basically what we're talking about. So what are the sort of things that GISs can do? Well, one of the big ones is analyze spatial data. And so when we talk about analyzing data, we're talking about taking raw data or information and converting it into knowledge. And that's actually a really powerful concept if you think about it. We just take information that may or may not be useful, data that may or may not be useful, things that we can't even understand, and we take these complicated things and we figure out how to make it useful. And that analysis, or analyzing data, if you will, is just basically the core of what we do. For example, you can look at, if you look at this coronavirus stuff, and you wanted to estimate resource needs, and you knew based on early data how different populations were affected. You could analyze census population data spatially across the country and figure out an estimate of the number of people who would be affected and at what extent. You know, how many people would need to be hospitalized and all that sort of stuff. You could then spatially plot out all the hospitals with the resources, and then identify the number of people who potentially have or will need hospitalization, and assign those people to the nearest hospital, and you could get some idea of where you're going to have shortfalls or not. We can also use GIS's capture data. This could be something as simple as taking aerial photos and digitizing and creating boundaries around things that we can see, or taking images that don't have a spatial component, like for example a screen capture of a weather map or something like that, and then converting it into a spatial feature. We can actually create things from scratch. We can manipulate stuff. It allows us to store information and to create visualizations and ways that we can show that. And all this is dependent on having spatial data. So a couple of key things. Number one, how do we copy or mimic reality in the digital environment? My standard answer for this is we do it very poorly. And the reason we do it very poorly is simple. Um, the world is a vastly complex and detailed place, and the GIS environment simply cannot reproduce it at that level. And so we make a poor facsimile of reality, but we try to make it accurate in terms of the things that we're interested in or need to understand. Um, what sort of things can we create or display? That's a really open-ended question. It depends. We have two data formats, vector and raster. Vector being points, lines, and polygons. Raster being a grid-based system. From that, we can do everything from images to multispectral data to um, points representing features to lines representing things like roads, and polygons representing stuff like counties or buildings. So there's lots of ways we can do it. How do we do it? We simply use one of these data formats to create an abstract rendering of reality in our GIS environment. So like I said, how do we do it? Very poorly, but we try. We do it by creating discrete objects and continuous surfaces, things like points, lines, polygons, elevation models, elevation surfaces, uh, temperature layers, slope maps, these sorts of things. And how can we do that? We can do it by creating vector and raster features in these vector and raster data formats. So let's look at some of these in a little bit more detail. When we talk about discrete objects, the world is a series of fixed objects with defined starts and stops. If you think about the discrete object view, in other words, you visualize the world in terms of discrete objects, then this is how the world exists. Fixed objects, defined starts and stops. In other words, it is one thing until it becomes something else. For locations, we use points. For one-dimensional objects, a one-dimensional object would be a thing like a line. Two-dimensional objects would be areas, that would be polygons. This, ladies and gentlemen, is vector data. Some more examples. Here we have a map of, I believe this is counties, and we have these rivers or roads, and we also have all these cities. And these are our representations of what these things are. They pale in comparison to what the features are in reality, but for the purposes of the kind of analysis we're doing, the sort of study that we want to do, the visualizations that we want to make, these are perfectly good renderings or representations. So when we think about the discrete object view, think of the world of digitized shapes, of outlines and things like that, points, lines, polygons, vectors. Here we have a football field in an image, and if we were to make a vector version of that playing field, we would simply have a polygon of it. Here's another nice map. This one is a Virginia Beach National Hydrography Dataset, where we have all these different line features representing different types of water bodies, and then we have polygons, so things like swamp marshes and reservoirs and playas and whatnot. And so all the various hydrologic features in the Virginia Beach area are represented in some form of vector data in this map as points, lines, or polygons. In this map, lines are polygons. So, the object view is not the only way that we can look at reality in the digital world. We also have to consider the raster format, and this is sort of a continuous field type view. So the key thing to remember is in this setup, in a raster is a grid-based data set, much like tiles in a floor or something like that, or like a big piece of graph paper, if you will. Every cell can only have one value. So whatever it is you're mapping, that's the thing. If it's land cover, for every cell it says what kind of land cover is here. If it's elevation, it's what's the elevation here in this cell. All the cells are the same size. That's how the grid kind of works. Oftentimes the easiest way to visualize this is to think of these pixels in a digital picture, because a digital picture is a raster format, and so that's basically how rasters work. In the example of a picture, we don't have, for example, what each cell is. We simply have a color value associated with each cell. And then collectively, the individual cells and their individual colors create the picture or the image. So this sort of illustrates kind of what a raster grid would look like. We have basically a grid, which is number of columns and rows, x's and y axis. Every cell has some bit of information in it. Here we have a really nice raster-based analysis of land cover. And so whatever this area is, they used some technique to examine aerial photos and multispectral information to figure out how or what the particular land cover for every pixel or every space in the grid, every raster cell was. And so in this example, they would look down and say, is it open water? Is it developed open space? Is it developed low intensity? Is it developed medium intensity? Developed high intensity? Is it barren ground, deciduous forest, evergreen, mixed shrub, grassland, pasture, cultivated crops, woody wetlands, emergent wetlands, etc.? And for each of these classifications, they would have some means of determining whether an individual raster cell was whatever. Once they've identified the best fit for everything, it gets assigned that color, and that leads to this map that you see on the right. So again, when we're looking at vector and raster data, they both contain attributes, and this is important. Attributes is the information about the spatial features. Vector is capable and designed for storing multiple attributes. It's like having an Excel table of information for every feature. The attributes are stored in tables. The tables come in lots of different types: nominal, ordinal, interval, ratio. These are some of the vocabulary terms you've been looking at, and so I'm not going to spend too much time going over, but you get the idea. Nominal, name, unique kind of thing. Ordinal, ranked. Interval, distance is significant. Ratio, non-arbitrary zero, etc. Here we have an ARC map document, and we have a states data set that has been displayed, and we have opened up the attribute table for that feature. And if we were to examine this table, it's just like any kind of a database table. We have tables, we have fields, and we have records or columns and rows, if you will. Any particular field is a type of information. Individual records are that information associated with a specific geospatial feature. In this example, we're looking at polygons, and there's a polygon for every state. And so, for example, polygon with FID number 0 is Hawaii. It's FIPS state number 15. It's in the Pacific subregion, and it also has a population number. And so all this information is there. And if you were to look at Hawaii, which is actually behind the table here in this example, you could click on that. It would light up Hawaii in the table, or you could click on Hawaii in the table and it would light it up on the map. Now, I want to point out something. It says 0 out of 51 selected, so we haven't selected any. How do we have 51 states? Well, we don't, but a lot of times with state data sets, they include the District of Columbia. So here's a more up-close look at a attribute table. Again, columns are fields and records are rows. Very much just like you would see in a lot of different setups, whether we're looking at individual sheets in a spreadsheet like an Excel file, or in an attribute. It's the same kind of setup: columns and rows, tables, or fields and records. Again, fields and records, columns, rows. More information there to tell you things about all kinds of interesting stuff. Now, here we have a nice map, and what do we see on this map? All kinds of data sets. If you look in your table of contents, underneath each entry you have a representation of what the data type is. Points show up as points, lines as lines, polygons are polygons. In this setup, all the data we have is vector data. You could select any one of those data sets in the table of contents there to the left, right click on it and open up the attribute table and see what information we actually have stored with those spatial locations and spatial features. Metadata is also something we talk about from time to time. Metadata is simply data about your data. Here in the US, metadata is organized by the FGDC, the Federal Geospatial Data Committee. They set the standards for content and format, and so they have laid out what data has to be in order to be compliant. Number one, it has to have a description of what it is. Number two, there must be some accuracy information, because data quality is defined as the fitness of a data set for an intended use. You can't determine if it's fit for a specific use if you don't know anything about its accuracy. Number three, there has to be some information on how the data is organized. What are the fields? How are they calculated? Is it a raster? What are the classification codes? What do the numbers mean? What are the symbols? That kind of stuff. You got to have some spatial reference information. Otherwise, not only do you not really be able to use it, you can't display it properly or do any kind of analysis. And so the spatial reference is really important. Obviously, the entry and attribute information in the tables is important as well. And so in the metadata, you need information about that to explain anything that's not just abundantly clear. And there has to be distribution information. What this means is who can use the data, how the data can be used, who has to be attributed for the data, etc., etc. So when we look at the different data that we're dealing with, there's a couple of things we need to consider, and I'm going to talk just briefly about a few of these, and then you can start on your lab assignment and redo any missing work, and that should keep you on track for next week. Coverages are a type of vector file that I call it an antique format. They're almost never in use, and we're basically just going to skip it and not really talk about it. The only time I've ever come across coverages is in textbook examples. I'm not saying they're not there, I'm just saying they are so rare. The likelihood that you'll have to deal with them is minimal, and if you happen to have to deal with them, honestly, you're just going to look it up in a book, in a resource online, in a help section to figure out what you need to do to change it, to modify it, to create something new out of it. Because otherwise, we're going to spend a whole lot of time teaching you a whole bunch of stuff that you're never going to use. Instead, we'll focus on things like shapefiles. Shapefile is a type of vector object. It's made of multiple files. They're really hard to move if you're not using ArcCatalog or some similar program, because a shapefile, notice how it says shapefiles, plural, it literally is more than one file. It's at least 5 files, and you have to correctly copy and move all 5 of those, or the shapefiles in ArcMap or another GIS software will not function properly. Okay, you lose one file out of that collection and it's not going to work. Now, when you look at this in the geospatial software, you don't see 5 files, you see one file. That one file has 5 components. When you look at geospatial data like this, using things like Windows Explorer, you see the 5 files. That's why we don't want to get into the habit of copying and moving around geospatial data using things like Windows Explorer. We want to move spatial data with a program like ArcCatalog. The other thing we're going to talk about is geodatabases. Geodatabases are basically the Esri format to place multiple vector types in a single file with the same spatial information for easy use and movement. Now, in terms of geodatabases, there are 3 basic types. We have a file geodatabase, we have a personal geodatabase, and then we have something called an SDE geodatabase. A file geodatabase is a geodatabase that is basically stored in a flat file structure. A personal geodatabase is dependent on having Microsoft access. Not access to Microsoft, there's a Microsoft program called Access. It's a database program. Personal geodatabases only function when you have Microsoft Access. They run off of it, and so that's a bit of a drawback. File geodatabases are more commonly used for that reason. But the SDEs are these big enterprise geodatabases. These are the ones that, like, for example, a city might use to store all their spatial data, and they have a lot of really cool features. You can go in and mess something up, and you can just basically unwind it back to before it was messed up. You can have multiple people working on the same file at the same time, and you won't get file locks. So there's a lot of distinct advantages to these SDE or enterprise geodatabases, but they're also a little more costly and stuff to set up. But that's the 3 types of geodatabases that we talk about. In general, the GIS environment, the GIS world, if you will, is moving away from things like shapefiles and coverages and into features and feature classes in geodatabases. This eliminates the multiple files because it goes from a linked setup where your shape, like the polygon, is related to the files individually, and more into a system where you have an object-oriented design where the spatial data, the attribute data, and the dimensional feature stuff is all sort of stored together. There are advantages to this system. The biggest one is that it makes it harder to screw up the data like it is with shapefiles, which can be really easy to mess up. And so as you move through the GIS program, we will spend in the future classes a lot of time in map where we will learn to get comfortable moving and using and copying and changing and editing shapefiles and geodatabases. When we move to ArcGIS Pro, that software is designed to function with geodatabases specifically, and so you will spend a little more time there dealing with this. But again, these are all things that are designed to make the workflow easier, seamless, and more accurate. So that, I believe, is all we have as far as the lecture goes for this week. Again, do your lab work. Watch the other videos that I have linked here in this week's folder. They'll provide additional information about the topics we've discussed tonight. And I look forward to next week. Hopefully, by then I'll have it set up to where we can actually do more interaction between us. We'll do some Zoom stuff so that if you have questions and things like that, I can answer them a little bit better than what I could, by email. We can have a conversation, if you will. So good luck, and again, if you missed an exam or you missed a quiz, I've posted makeup quiz and makeup exam links, and they are only eligible for people who didn't take those things. And so, if you see it there and you think, "Oh, I took the exam, why is it still there?" If you took the exam, you're good. If you have a grade on the exam, you're good. This is for people who missed those classes. All right. Good luck. Stay virus free. Practice social distancing. Um, Wash your hands. Don't touch your eyes. Yeah. Hygiene. Vitamins. Oranges. Don't hoard raw materials. Don't try to buy up all the toilet paper and ramen noodles. Just be good people and we'll get through it.